Hi, everybody. In this video, I want to talk to you about an extraordinarily important concept for an astronomy class, and that's the reason for the seasons. I'm going to be working without a slide deck. I'm going to be using a simulation in this video, but I'm also going to be talking to you for a little bit. And I want to go ahead and start by addressing a common misconception. Most people, or a lot of times, people think that the seasons are caused by sometimes the sun, or sometimes the Earth is closer to the sun and sometimes the Earth is farther away from the sun. While this is true, Earth's orbit is very, very, very close to circular, just barely not circular. So yes, our distance away from the sun varies a small amount during its orbit around the sun, but not by much. And we can dispel the idea that it's the distance away from the sun with a few salient observations. One of them is, if we were to consider the seasons on the Earth, most of us are aware of that when it's summer in the Northern Hemisphere, it's winter in the Southern Hemisphere. So right now, it's summer here in Knoxville, about to be fall. If we were to go down to Australia, it would be winter, about to be spring. The seasons are opposite. You can't really explain that with a distance away from the sun argument. Another one that just really blows that idea out of the water is that the Earth is physically closest, what we call the perihelion point, its nearest approach to the sun, in January, which is clearly winter for us. And that's when the Earth is closest to the sun. So it cannot be the distance from the sun argument. So if it's not the distance from the sun argument, what is it? And this one, it really comes down to is every time that you look at a globe of the Earth, you'll notice that it's tipped over. It has this tip of 23.5 degrees. It's what we call the axial tilt of the Earth, that its rotation axis. You can see the Earth rotates from a point directly through the South Pole, geographic south, to the geographic North Pole, and that's what the Earth rotates about. And it's tipped over 23.5 degrees. What do I mean by tipped over? Tipped over with respect to what? So if directly off camera that way would be the sun, so Earth would be orbiting around on a flat plane of the bottom of the screen here. So the bottom of the screen will be the plane that it orbits around the sun. No axial tilt, it would stick straight up and down. So we would have the plane of the solar system, the orbit of the Earth, be moving around on a tabletop at the bottom of the screen. And if Earth had no axial tilt, it would be sticking straight up and down with respect to that. But it's not, it's tipped 23.5 degrees. One of the key points about this is as the Earth orbits the sun, the North Pole will always point in the same direction towards Polaris. You'll have to go review some of the slides to see that a little bit better. I don't have enough room to really move around right here. But what I do have is a wonderful simulation that can show you a lot of these same things. And I think it does a very, very good job of helping explain the seasons. So what you're seeing on your screen right now is an astronomy simulation developed by the University of Nebraska-Lincoln. I have links on Canvas of how you can go download or just access the flash versions of these. So you can play with these simulations, and they'll be great for the seasons to help you review the seasons, but they'll also be great for future topics in the class. And every once in a while, I'll be showing these in my videos. So let's take a look at the seasons as the Earth orbits the sun. So it's this revolutionary motion around the sun, the fact that it's orbiting the sun, plus this axial tilt that gives us the rise of the seasons, why we have hot summers and cold winters. We're going to start with the Earth and sun over here in this position. You can see right here, it has its axial tilt of 23.5 degrees. And right now, the North Pole is tipped directly away, and the South Pole is tipped towards. So it's tipped, the North Pole is tipped away from the sun, the South Pole is tipped towards the sun. That would be a scenario where if you are the sun, you'd be looking at the Earth like so. So notice that the north is tipped away from you, but the south is tipped towards you. All right. So now that we know where we are in the orbit, let's talk about these other two windows. This window right here is showing you the day side and the night side of the Earth. The person represents where you're observing from. I've set it to be very close to Knoxville at about 36 degrees north. So that's the latitude it's at. And this red line, not only showing you the latitude, but it gives you a sense of day versus night. How much of this line is in the daylight versus how much is in night gives you an idea of the ratio of daylight hours to nighttime hours. So here, daytime hours will be short, nighttime hours will be long. In the winter, the days are short. Also notice that for the southern hemisphere, it's the opposite. So here, the southern hemisphere is tipped towards the sun. So they would be having longer days and shorter nights. Oh, the axial tilt, that quickly is starting to explain why it's going to be winter in the north and summer in the south. Great, perfect. All right, so this is showing the direction that the sunlight's going to be coming in with respect to the Earth. And right here is going to show the sunbeams, the sunlight, as it falls onto the surface of the Earth. Notice that they're coming in at a low angle. In the winter in the north, the sun's really high or really low in the sky. And that makes the light spread out over a wide area on the ground. So the light is less concentrated. And this is one of the reasons that winter is cold. It's not only that we have long nights and short days, but the light is really spread out. And the light is carrying energy, the energy that warms the surface of the Earth. And if we spread that energy out, then it can't warm up the Earth as much. Okay, so now we know, here we have our orbital view, here we have our day-night view, and here we have the rays of the sunlight coming in, and we can see they're coming at a low angle. I'm going to go ahead and start the animation. We're starting on December 21st, the winter solstice, when the North Pole of the Earth is tipped away from the sun, and the South Pole is tipped towards the sun. I'm going to start the animation, and I'm going to try to stop it at all the changes of the season. So as you can see, as it's moving in its orbit, this is remaining tipped in the same direction, pointing out the north towards Polaris. You notice that the sunlight is coming in more directly, and go ahead and stop. We'll go back a couple of days to right about here, about the 21st or 22nd of March, which is also called the spring equinox. Notice now that, again, if you are the sun, I'll orient the Earth in the same way that you can see in the simulation. If you look up at my little video, you can see that right here we'd have the Earth spinning around. And yes, it's still tipped 23.5 degrees, but it's not tipped towards nor away from you, the viewer, in the screen. It's tipped in a different direction. So as the Earth rotates around, we would have it so as it rotates around, we have every part of the Earth is getting equal days and equal nights. And at that equal days, equal nights, let's say the equal nights part in Latin, equinox, that is where we get the equinox from. And we're going from northern winter towards northern summer. So this would be our northern spring equinox, and the date is about March 21st, March 22nd. Notice that the sunlight is a little bit more concentrated. I can take a look at the sunbeam spread. So this is just showing how spread out the light is. So make a mental note of where the boundaries of this are, spilling a little bit over right here. And then we'll take a look again at the summer. Also notice that always half day, half night, as the Earth rotates around and around and around, all parts of the Earth have half daylight, half nighttime. Let the simulation keep going. Now we're going towards northern summer. Notice that the sunbeams are now hitting, their subsolar point is now concentrated in the north. Go back to our sunbeam angle and get ready to stop whenever the pole is pointed directly towards the sun. Go back a couple of days. So here at the 21st of June, now we have the North Pole is tipped towards the sun. The South Pole is tipped away from the sun. We have very long summer days, very short summer nights. The sunlight is coming from nearly overhead. So the sun is very high in the sky, and the sunlight is very concentrated which is very good at warming up the Earth. So we have a long day and concentrated sunlight, the double whammy of warming up. So we have hot summers. And now you can see, oh, this dot is now a little bit smaller. It was spread outside of these lines before. All right, so, oh, and I should do the view for you. So in this case, the northern hemisphere would be tipped towards you, and the southern hemisphere would be tipped away from you if you are the sun. And then the Earth would rotate like so. Notice that the North Pole is in constant daylight, what we call polar day. And the southern hemisphere is in constant nighttime, what we call polar night. 0 hours of daylight down here, 24 hours of daylight up here. All right, let's continue with our animation. We're going past summer. It should be cooling off. So the sunlight should be spreading out. It should be coming in at a lower angle. And that's exactly what we're observing. And I'll go ahead and stop it whenever we hit the fall equinox, which is right about there. Go forward just a little bit. On the 21st of September is about when the fall equinox occurs, coming up very, very soon. The sunlight's less concentrated than it was in the summer, so it's going to be cooling down. And notice that we have equal day, equal night, and it doesn't matter where on Earth you are, equal day and equal night. Close enough. And we can look at our sunbeam spread, very similar to what we saw at the spring equinox. Notice that this part is spilling over these blue lines right here. And now we'll let it go back to winter. It's going back to winter. The sunlight is less concentrated in the northern hemisphere. Our days are getting shorter, our nights are getting longer, and eventually we'll be back at the winter solstice on the 21st of December. And we've done a full cycle of the seasons. Go ahead and look at how it's spread out now, and you can really see that that sunlight is less concentrated, spread out over a larger area of the ground, making it colder in the northern winters. Notice it's the opposite in the southern hemisphere, so let's just move this person on down to the southern hemisphere. Sunlight's much more concentrated. So while it's northern winter up here, it's southern summer down in the southern hemisphere. All right, so that's my demonstration for the seasons. Hopefully you found this illuminating and a good supplement to the slides, which I'm sure you have already gone through and read. And this added just what you needed so you can fully grasp understanding what the seasons are and why we have the seasons. Just a little end note, the reason for the seasons, it's not Christmas, it's the axial tilt of the Earth.